Okay, today we're going to be talking about rotations, which is a third type of transformation in our unit. We want you to be able to learn to draw and identify rotation images of figures, and that will be quite an interesting process to talk through. Okay, so as we explore rotations, I really want to take a look at this graph of this triangle EAR. Okay, and if you were to graph these points on a piece of paper and put them, of course, they're in the first quadrant, okay, and then you turn your paper once to the left or to the right, it doesn't matter, and then pretend like, and that's a 90-degree turn, either to the left or to the right, and then pretend like you're still looking at the first quadrant with the next quadrant that's facing you, and graph those points again as if that were the first quadrant, and keep doing that until your image is rotated into all four quadrants. What you would have is a rotation, okay? So you could literally just pretend like each quadrant is the first quadrant as you rotate your paper 90 degrees, and that's how we graph rotations. So what it gets us is this point E could be, which is 2, 5, becomes 5, 2, and, sorry, 5, negative 2. And so there's a little pattern that happens with all these points as we rotate them from quadrant to quadrant. But if you have the idea of what we're doing, and I'd like you to actually do that on a piece of paper at home before you get to class, with rotating that paper and graphing as if the quadrant in that rotated paper is the first quadrant, then that will help you make sense of what actually we're doing with these rotations. So what happens with these is we have a shift that takes place with our original XY coordinates. So if our coordinate is, let's give us an example here, let's say our coordinate is the point 2, 3, and that's all in the first quadrant. When we rotate that point into 90 degrees into the next quadrant, that point will become 3, negative 2. Okay? Those points switch back and flip signs from the original to become negative 2, negative 3 as it's rotated 180 degrees. And then the final rotation, 270 degrees, will give us the point negative 3, positive 2. So you can see that when you have your original point and the rotation of 180 degrees, they are just negatives of each other. And 90 and 270 are negatives of each other too. And the points X and Y switch places. Okay, so that's how the rule goes. And also some patterns that you might notice are that whether you rotate clockwise or counterclockwise, rotating 90 degree clockwise is the same as rotating 270 degrees counterclockwise. Okay, and so what we have are images that can potentially lie on top of each other depending on how many times they're rotated. And that's an important concept for when you get to trigonometry. So, is a rotation an isometry? Yes, it is. A rotation turns an image, but it does not resize it, so therefore our rotated images are still congruent to the original pre-image. Okay? So, if we have this point P and we rotate it clockwise, which we consider to be a negative rotation, then P prime is still exactly like P, it's just rotated. Okay? Of course, we can't have congruent points because points, don't have any size to them, but you get the picture. Let's see. A counterclockwise rotation is actually what we consider to be a positive rotation, a rotation in the positive direction, and so P becomes P prime after that rotation is made. Now, a good way to remember what positive and negative direction is to look at our coordinate plane and how we name our quadrants. Quadrants 1, 2, 3, and 4 are named in that order. And that is the direction, increasing in number, of positive rotation. Okay? Negative rotation goes down in number with quadrant name. Okay, so that hopefully will help you remember a good way for positive and negative rotation. Because if you say a rotation of like 50 degrees, that's in the counterclockwise direction, but a rotation of negative 50 degrees would be in the clockwise direction, which is counterintuitive until you remember the quadrant naming convention. So, a good way to really be able to see what's happening is if we actually rotate things on polar coordinates. And that enables us to rotate things in degree measurements other than 90, 180, 270, that kind of a thing, okay? But most of the time things aren't graphed in polar coordinates, which is fine. You know, you can convert them, and we're not really concerned that you know how to convert them, but that you have an easy way to rotate things. So, let's put a figure in here. And here we have this little triangle. And we have triangle, we'll call it A, B, C. And let's say that I want to rotate A, B, C. Let's see. I've got measurements here of 15 degrees. So let's say I want to rotate it 45 degrees. Now, positive 45 degree rotation is going to be in this direction, okay? So I'm going to head to the left here, 45 degrees. So 15, 30, 45 means I'm moving 3 radial degree measurements, or not 3 degree measurements over. So A prime would be here, B prime would be here, and C prime is here, okay? So that is the same triangle, it's just rotated a little bit, okay? Now let's say that I wanted to rotate it, let's see, I don't want to put that in blue, I'm going to put that in green. I want to rotate A, B, C by negative 75 degrees. Well, that means I'm going to have to go in this direction. And so 15, 30, 45, 60, 75, that's a total of 5 measurements away. So point A is going to be 1, 2, 3, 4, 5. So A double prime will be here. B 1, 2, 3, 4, 5. B double prime will be here, and C 1, 2, 3, 4, 5. C double prime will be here. Okay, so here you see now 3 different representations: pre-image, triangle ABC, and then the other 2 rotated images in the coordinate plane, in the polar plane, I should say. Okay, so here's another example. Here we have quadrilateral shoe, okay, S-H-O-E, and this quadrilateral is in the second quadrant here. When we rotate this quadrilateral, it will be 180 degrees clockwise. So clockwise. It's a negative rotation, but that doesn't matter. It's the same as if it were a positive rotation because it's 180 degrees, and that's half of 360. So what happens is my coordinates stay the same, x, y order, but they also are negatives of each other. So if it was negative here before the rotation, after the rotation it's positive. Negative or positive before the rotation means it's negative after the rotation. Okay? So using that chart is a neat way to just quickly rotate a set of points without having to consider much of anything else. Now, another thing we want you to be able to do is identify a rotation image. And a rotation image will always have that prime notation, okay? So that's an important thing to do. And another thing we want you to also be able to do is when we have a regular polygon, in this case we're going to use an octagon, we want you to be able to rotate that onto itself and figure out how many degrees it would be to get, like, say, point D here, to lie atop maybe, say, point B. Okay? So we want it to be a perfect amount of rotation. Well, that takes a little bit of thinking, and it's slightly related to what we did in the last chapter. So if I have a center point of a polygon, and I divide everything up, all the vertices up, like this, then what I really have is 360 degrees around here that's divided up into the number of vertices. So 360 divided by that 8. It gets me a number that allows me to calculate how many degrees I need to move a vertice. Okay? So 360 divided by 8 is 45 degrees. So if I wanted to rotate D to lie atop point B, rotate that polygon, I would have to rotate it 2 segments of 45 degrees. Okay, so it would have to be a total of 90 degrees. Okay. Now, another thing we wanted here was to name the image of D under a 270 degree rotation. Well, since we know that if we're going to have it lie atop each other, that we need to divide it by 40 increments of 45. 270 divided by 45 is 6. And so we can count 6 over. So 1, 2, 3, 4, 5, 6. So a 270 degree rotation would make point D lie atop F. So the image of D under a 270 degree rotation is F. Now, the next thing we want to do is name the image of E under a 405 degree rotation. So doing that same thing with 405 divided by 45 yields 9 vertices that we're going to have to go through. Well, we know that 8 of them are in one rotation. So we're going to have a full rotation of 8 plus another one. So the image of E under a 405 degree rotation is going to be D. Okay, so we're just spinning this polygon on top of itself in increments of 45 degrees, only because this is an octagon. If it were a triangle, it would be increments of 60 degrees. Or no, 360 divided by 3 would be 120 degrees. Okay, so that would be how much we need to spin it so that the vertices lie on top of each other. Okay, I hope that makes sense. If it doesn't, I will go over this with you again in class. Another thing we need to consider is composition of rotations. Rotations can be added or subtracted. So if we have a 45 degree rotation followed by a 30 degree rotation, that's a combined rotation of 75 degrees. Okay, and we have to make sure we note what direction these rotations are taking place. So if it doesn't give a sign, assume it's a counterclockwise direction because it's positive. Because negative rotation takes place in the counterclockwise, or in the clockwise direction, sorry. A negative 45 degree rotation followed by a positive 30 degree rotation would be a total rotation of negative 15 degrees. Because that's negative, we need to know that it's in the clockwise direction. Okay? It's very important. So what we've learned what a rotation is. We've learned that positive rotation happens in the counterclockwise direction, negative rotation is in the clockwise direction. We've learned a little bit about rotating regular polygons onto themselves, and this happens in degree increments that are equal to the measure of not one interior angle, of 360 divided by the number of sides, okay? So if our triangle has, or if our figure has 4 sides, we would divide it by 4. If it has 7 sides, we would divide 360 by 7, and that gets us the degree increments that we can rotate. And we can also add and subtract rotations to get a net rotation, and that rotation can be either positive or negative, okay? And I'm sure you're going to have lots of questions on this in class. We have an investigation we're going to do, and you have a choice of several worksheets depending on what you understood least, or best. I would prefer you do the ones that you understood least, more than the ones that were easy for you. Okay? So, we will see you in class.